right? Consider a spring block system, spring having a spring constant K and block having a mass M placed on a smooth horizontal surface. Fine. Now, like in laws of motion, work energy power, we had come across questions like this. Now, this block experiences some forces. Its weight will be acting, normal force from the surface will be acting. And if the spring is stretched or compressed, spring force will also be acting. Now, if you visualize the forces on this block, weight acting downwards and normal force acting upwards, they will balance. Spring force, which may act to the right or to the left, will not be balanced. If it acts, it will not be balanced. Okay. Now weight and normal are anyway balanced. Suppose the spring is at natural length. Let's say this is the natural length of the spring. Okay, NL stands for natural length. Then the spring will not be exerting any force on the block. So Aishwarya, you tell me, if we leave the block from this, if we release the block at this position from rest, will it start moving or will it just stay there?
Sir, it will stay there.
It will just stay there because the net force on it is zero. Okay. So, fine. Let's not give it any name yet. But if we release it from this position, it is not going to move. Okay. Suppose the spring is stretched a little bit. Let's say the block is taken to this position. Assume it is moved, or assume the spring is stretched by a distance x. If the spring is stretched by a distance x, then the spring force acting on the block. The formula for spring force we know is F is equal to minus kx. Minus indicates direction, but since we have already indicated the direction here, you can say the force F here is equal to kx in magnitude. Okay, as a vector, if you want to write, then you will write it as minus kx. Fine. Now, what are the forces acting on this block? Its weight will be acting, normal force from the ground will be acting, and now there is a spring force also. Now, weight and normal force will balance, but spring force will not be balanced. So, what happens if we release it from this position? Suppose it is released from rest here. Then under the influence of spring force, it starts accelerating to the left. Starts accelerating means what? It gains velocity. Initially it's at rest, but it will gain some velocity to the left. But spring force will continue acting on it. As long as the spring is stretched, the spring force will continue acting on it. So it will gain some more velocity. It will become faster. And after some time, the spring will come to natural length. But by the time the spring comes to natural length, the block would have gained some velocity. So due to its inertia, it will continue to the opposite side. Now, when the block goes to the opposite side of natural length or of mean position, we can say. Mean position is the position where net force is zero. We have already identified that position. Okay. For a horizontally oscillating spring block system, the natural length of the spring itself is the mean position. So once the block reaches that mean position, it will have some velocity. It will cross to the other side. And when it goes to the other side of natural length or mean position, the spring is compressed. Compressed spring will start exerting a force in the outward direction. So the block will slow down. It will further slow down and stop somewhere on the other side. Okay. Let's say it started from here and it stopped here. We'll see if it covers the same distance on both sides or not. We'll have to prove all of that mathematically. So here the velocity of the block is 0. Here also the velocity of the block is 0. Now, the left side of natural length where the velocity becomes 0, the block momentarily comes to rest. But the spring will be in a compressed state when the block is at, okay, let's name these positions. Let's say the starting position is A, this final position is B. When the block is at B, momentarily at rest, the spring will be in a compressed state. So it will start pushing the block outwards. As a result, what will happen? The block will start gaining velocity to the right. Again, when spring reaches natural length, by the time the spring reaches natural length, block would have gained some velocity. It will cross to the other side. And on the other side, it will slow down and stop. So it will perform oscillations. This system will perform oscillations. Okay. So we have considered a simple spring block system placed on a horizontal surface, and we have visualized that it will perform oscillations. Now, what we have to do is derive the time period of oscillation first. Okay. Generally, how do we derive time period of oscillation? Remember these steps, all of you. Okay. All three of you have joined. Fine. Steps to determine time period of oscillation of a system. First thing is you need to check whether it executes SHM or not. Fine. As far as your syllabus is concerned, you will only need to know how to how to calculate time period of systems executing simple harmonic motion. Okay. Now, how do you check whether system is executing SHM or not? You have to write an expression for net force. Let me write it this way. Express net force acting on the oscillating object in terms of displacement from mean position. X stands for displacement from mean position. You have to express net force in terms of that. And if net force is negative of some constant multiplied with displacement, then it is SHM. Okay, that's the first thing you need to do. Next, once you do that, you get omega. Omega is under root k divided by m. And then you get the time period, simple. See, if it is executing SHM, it can be represented by that sine function, no? And the period of repetition of that sine function would be 2 pi by omega. So time period becomes 2 pi under root m by k. These are the steps to derive the time period of oscillation. Okay. Now let's see if the given system, this spring block system, first of all executes SHM or not. Okay. Now we have identified the mean position for this system. The natural length of the spring itself is the mean position because at that instant, means when the spring is at natural length, the block will not be experiencing any net force. So the position where net force is zero, that position is what we call as mean position. Okay. Assume the block is displaced by some distance x away from the mean position as shown in the diagram itself. Okay, let's say it is displaced to the right. Now, if you displace it to the right, the spring is stretched. So you know that the block will be experiencing a force to the left. And spring force by definition is given by this formula. Fine. Where K is the spring constant. In case of spring force, K is the spring constant. Therefore, this is definitely simple harmonic motion because it satisfies the condition for SHM. F is equal to minus Kx. In the condition for SHM, F net is equal to minus Kx. K is called the force constant. When it comes to a spring block system, in place of that force constant, you get the spring constant itself. That's all. Okay, so this definitely executes SHM. And K here is the spring constant. Then you can easily tell the time period. Time period simply becomes, or okay, let's do it step by step. Let's calculate omega first. Omega will be under root K divided by M, where K is the spring constant of the spring now, and M is the mass of the block. Then from that you can say time period is 2 pi under root M by K. That's the time period of oscillation of this spring block system, where M is the mass of the block and K is the spring constant. Hope this is clear to all of you. Remember the steps to derive the or determine the time period of oscillation of a system. First, you check whether it is SHM or not. In that checking process itself, what you will automatically do is get force in terms of displacement. Fine, that is how you check whether something executes SHM or not. And when you write force in terms of displacement, if you see that it is in this form, F is equal to minus some constant into X, treat that constant as force constant. So in case of the spring block system, the spring constant itself was in that place. So spring constant became the force constant. And then you get omega under root k by m. Mass of the object has to be given. Okay. And then you get the time period. Fine. So we have determined that this spring block system executes simple harmonic motion. Let us work further on that. We know where the mean position is. Let's assign some values this time. Assume spring constant is 200 Newton per meter. And let's say the mass of the block is some 2 kg. Okay. It is pulled aside, let's say by a distance of how much shall we take? 20 centimeters. Let's say the spring is stretched by 20 centimeters and the block is released from rest. Okay. Now we have visualized what happens to this system. After you release this block, the spring force will pull it to the left. It will gain velocity. Okay. Here it is at rest. Fine. It will gain velocity when it reaches the natural length. When the spring returns to natural length, the block would have gained some velocity by then. Determine that velocity. We'll discuss different ways to do that, but I want you to try it first. So in some time, you know that the spring will come to natural length for the first time. Situation will be like this. By then, the block would have gained some velocity. Okay. How to find that out? Think and tell me an approach, all of you. I'll give you 1 minute. Fine. Listen, we know that spring force is a conservative force, and this block is moving because of spring force only. Weight and normal force are balanced. As this block oscillates back and forth, the only force doing work is spring force, which is conservative. And if work done by non-conservative forces is zero, you can use mechanical energy conservation. Initially, when the block is released from rest with the spring in a stretched state, the mechanical energy of this system is stored as potential energy in the spring. So in the initial state, the spring has potential energy. But later, when the spring returns to natural length, at natural length, the spring does not have potential energy, but the block is moving. The block has kinetic energy at that instant. And in this process, because spring force is the only force doing work, mechanical energy of the system is conserved. You can use mechanical energy conservation to find out the velocity. Okay, or speed of the block at that instant. But we had done those problems in work energy power. That's fine. You know, I mean, you can revise how to do that. As Vanilla suggested, let us now consider this as simple harmonic motion and use the equations we derived in SHM. Now we have already checked that this system will execute simple harmonic motion. Okay. Listen, we know the natural length is the mean position in this case. That also we have determined. You have to imagine the system moving and identify the position where the net force on it will be zero. That position is the mean position. Okay. Now the block was displaced by 20 centimeters from mean position and released from there. So that 20 centimeter displacement, at that 20 centimeter displacement, because the velocity is zero, you can say that this position is the positive extreme of the oscillation. At extremes only, no, in SHM, at extreme positions only, the velocity becomes zero. So at whichever position the velocity is zero, that has to be an extreme position. Okay. So we know the mean position, we know the extreme position. The distance between them is what you call as amplitude, which in this case automatically becomes 20 centimeters. So this block, you know, it oscillates. Now we have visualized that already. This block, when it oscillates, it will oscillate with an amplitude of 20 centimeters. Now, how did we conclude that 20 centimeters is the amplitude? We knew the mean position and we knew the position where the block is at rest. That is the extreme position. So we can say that it will oscillate with an amplitude of 20 centimeters. Suppose the block had some speed here. Let's say it was already moving. Then this position is not the extreme position. Then 20 centimeters will not be the amplitude. We'll also see how to deal with such situations. Okay. So in this problem, the initial velocity is 0 here. So amplitude is 20 centimeters. We know amplitude. And what Vanilla suggested is we use the equation V is equal to omega root a square minus x square to determine the speed. Okay. To be able to use this equation, you first need to know, okay, we have derived amplitude. Next, we need to know omega. And we already discussed how to get omega of this system. It's a simple oscillating system with force constant as the spring constant itself. So K is known to us and M is known to us. Omega is under root K by M. K is given as 200 Newton per meter and mass of the block is 2 kg. 200 by 200 under root is 10 per second. So omega is known to us. Next thing you need to know is X. In the equation, V is omega root A square minus X square. X stands for displacement from mean position. Now, where do you want to know the speed of the block? When it is at mean position. So in this case, X becomes 0. When the spring returns to natural length, you are asked to find out the speed of the block. Spring returning to natural length means block coming to mean position. At that position, you want the velocity, so X becomes 0. That's all. So in this case, the speed simply becomes omega root A square. Root A square is A. So speed becomes omega multiplied with A. Omega we have determined is 10. Amplitude is 20 centimeters, that is 0.2 meters. So on the whole, it is 2 meters per second. That is the speed of the block when it reaches the mean position or the natural length. Okay. Had you solved this using mechanical energy conservation, you would have written something like this. Initially, the mechanical energy was in the form of energy stored in the spring. Energy stored in the spring is half k x square, 0.2 whole square. Finally, it gets converted to kinetic energy of the block because you wanted its speed when the spring comes to natural length. No, at natural length, spring won't store any energy. So all of it gets converted to kinetic energy of the block, half m v square. Just equate these two. Half and 2 get cancelled. This becomes 100. 100 into 0.2 whole square. 0.2 whole square is 0.04 into 100 is simply 4. So you get v square is equal to 4. That also makes v 2 meters per second. So if speed is what you want to calculate, you can use energy conservation. You can use ideas from SHM as well. Okay. Is this clear to all of you? Any doubts so far? Fine. So speed part can be taken care of using energy conservation as well as SHM ideas. How to apply SHM idea we have just learnt. Now I want you all to try this. Find out the time taken by the block to reach the mean position for the first time. This we had not done in energy conservation or any chapter before. Okay, we never involved time in the questions. But now, since we know that this system executes simple harmonic motion, we will be able to talk about time taken to move from one place to another as well. Okay, so just a moment, I'll copy this diagram. You know the force constant, you know the mass, you even know the amplitude. Okay, fine. I think there are many other things that you can find out. First, write the displacement as a function of time. Write the displacement time equation for this oscillating system. See, the general displacement time equation for SHM will be A sine omega t plus phi. You just have to plug in these values. How much is A, how much is omega, and what is the phase constant, depending on its initial position and how it is moving. Okay, we had discussed this also, how to write the phase constant. So recollect those ideas and write the position time equation for displacement time equation for this block. And then you calculate time taken to reach mean position for the first time. Okay. Do this all of you carefully. Right. We have already calculated the amplitude. Like it is obvious from the given situation. Distance from mean position to extreme is what you call as amplitude. Amplitude is 0.2 meters here. Okay. Omega is under root k by m. Omega is 10 radians per second, or simply per second you can write. Next thing is phase constant. Now this object initially means at t equal to 0 is at the positive extreme. Assuming it is oscillating along the x-axis, assigning mean position as x equal to 0. Okay. This particle, this oscillating object initially is at the positive extreme. Now when you are writing the sine function and the object is initially at the positive extreme, the phase constant to be used is plus pi by 2. Fine. Or you could have done it like this also. How to determine phase constant? Phase constant depends on the initial position and direction of motion of the object. Initial means at t equal to 0, where is the object and which way is it moving? What is its velocity? At t equal to 0, this object is at positive extreme plus a. So in the general equation, x is equal to a sine omega t plus phi. At t equal to 0, the position is, or the displacement is, plus a. Cancel a and a, you get 1 is equal to sine phi. Sine of what angle is 1? 90 degrees. So the phase constant becomes pi by 2. That's all. So that's the equation, displacement time equation for this object. 0.2 sine omega is 10, so 10t plus pi by 2. Okay. Next, the time taken to reach the mean position for the first time. This we had solved yesterday also. To get to mean position for the first time, basically what has to happen is the object has to finish one fourth or complete one fourth of the oscillation. Starting from extreme position, it has to come to mean position. It should do one fourth of the oscillation. So the time taken for that part will be one fourth of the time period. Time period is how much? 2 pi by omega. 2 pi divided by omega is 10 here. So one fourth of time period is one fourth of 2 pi by 10 becomes pi by 20 seconds. That's the time it takes. Now the time part we never solved in loss of motion or work energy power, because determining time from basic equations like acceleration time equation or velocity time equation will be very difficult. Okay, you'll need to do like whatever integration we did while deriving this general equation for SHM. No, all that integration you would have had to do in loss of motion if you want to derive time. This is the only way you can derive time period or time taken to move from one place to another. Okay. Now, since we have checked that this object executes SHM, we can say that it will get displaced to the same distance on the other side of the mean position as well, and then oscillate back and forth like that. It will keep oscillating forever in an ideal case. If there is no friction or air resistance, heat losses, it will keep oscillating forever with the same amplitude. Okay. So today's worksheet, you will have some questions based on this. So what have we discussed so far? A horizontally placed spring block system on a smooth surface. We know, like we have proved that it executes SHM. Now you know how to write the displacement time equation and tell time taken to go from one place to another. What is its speed at some position and such things. Okay. But you will have to work more on it. Okay. So solve the problems that are given in the worksheet. Next, consider a vertically suspended spring block system now. Suppose there's a rigid support like this. And let's say a spring is suspended. Fine. Assume this is the natural length of the spring. Just a moment. Yeah. Let's say this is the natural length of the spring. Now we assume springs to be light, massless. So let's say this is also a massless spring itself. Spring constant is K. We'll see if in this case also K itself becomes the force constant or not. For now, let's call it as spring constant. And the block of mass m, let me copy the block. Okay, fine. The spring was at natural length. Let's say we attach a block to it now. Yusuf, tell me what will happen after the block is attached and released. The spring was hanging at natural length. Now we connected a block and released it. What would happen?
So because of the weight of the mass will go down.
Good. Because of its weight, it will go down. At this moment, at natural length, will there be spring force acting? Yusuf, when the spring is at natural length, will there be any spring force acting?
So without the mass or with the mass?
Does it matter? Spring force depends on whether the spring is stretched or compressed or not, right?
So at natural, it's not stretched. So it's
At
not
natural
the.
length, it's neither stretched nor compressed, so there won't be any spring force acting, but there will be mg acting on it. Therefore, at natural length, the net force on the block is non-zero. So this time, natural length is not the mean position. Okay, mean position is the position where the net force on the object becomes zero. So this will not be the mean position this time. Okay. So if we release this system from here, we know it will go down because mg will dominate. There's no spring force, but weight is there. And in a real life situation, you would have observed the spring block system oscillates for some time and the block finally settles at some position. That position where it finally settles is the mean position. Now, when will the block finally settle somewhere? It will settle where the net force is zero. The block definitely experiences weight always. Okay, and weight mg will be acting downward. Spring force has to balance the weight. At that position, the net force will be zero. So let's say this is the position where F net is zero. Weight acts in the downward direction. So spring force must be acting in the upward direction to balance weight. That will happen, or that is possible only if the spring is stretched. So at this position, there will be some spring force acting upwards and weight of the block will be acting downwards. These two should be balanced. Wherever they are balanced, that is called the mean position. That position is called the mean position. And at mean position, the spring is already stretched. We had solved questions like this also in work energy power. Okay. Now, let's say that stretch in the spring is x naught. Okay. In work energy power, we called it as equilibrium elongation. Equilibrium means what? Net force being zero. For net force to be zero on the block, how much the spring should be elongated is called equilibrium elongation. Let's call that as x naught. We can even write an equation for it. At equilibrium, spring force, that is kx naught, balances mg. Therefore, the equilibrium elongation is mg by k. Okay, so we know how much the spring has to be stretched when the block is at mean position. Fine. Let us visualize that system now. Just a moment. You all can note this down. Equilibrium elongation is mg by k. Mg is balanced by spring force kx. So x becomes mg by k. Fine. Suppose you release the block at mean position. Let me mark mean position here. This orange dotted line is the natural length. The We'll take a green dotted line. This is the mean position for us. Okay. At mean position, we know the forces are balanced. So if you release it from this position, if you release the block at this position, the mean position, it's not going to move at all. You pull it below the mean position and release, it will get pulled upwards. Okay, anywhere below mean position, if you release it, basically what happens? Spring force will dominate. So there will be a net force in the upward direction. Anywhere above mean position, you lift it up a little bit and then release. Anywhere above mean position, mg will dominate. So the net force will be in the downward direction. So you can see that the net force is always trying to bring it to a particular position, that mean position. So there is a restoring force in this case. And that is why this system oscillates. So whenever you are asked to find out the time period of oscillation of a system or anything about oscillations, you should first visualize it like this. First thing to do is find out where the mean position is. And from there, you imagine the system to be displaced. Then you will be able to see that there will be a net force acting on it towards the mean position. You'll be able to see that there will be a restoring force acting on it. So this block definitely experiences a restoring force, and that is why it oscillates. Now we have to check whether this oscillation is also simple harmonic or not. The previous case we dealt with was a spring block system on a horizontal surface. Their weight was balanced by normal force. So weight didn't have any effect in that oscillation. But this time, due to weight itself, the mean position got shifted. Natural length is not the mean position. So this time gravity will definitely have some effect. As the block moves up and down, gravity does work also. Horizontal oscillations, will not do any work, but vertical oscillations, it will do work. So you need to check whether this is simple harmonic or not. Now, what are the steps to check whether it is simple harmonic or not? You need to express the net force acting on it as a function of displacement from mean position. Okay. The condition for SHM is F is equal to minus kx, where x is displacement from mean position. Okay, it could be x, it could be y also. In this case, the oscillation is in the vertical direction, so we'll write it in terms of y. Okay, that's not a big deal. The force and the displacement should be directly proportional to each other. That condition we have to see. Okay, now listen carefully. X is displacement from mean position. We have already identified the mean position. At mean position, the spring is already stretched by some distance x naught. Let that x naught be as it is. We'll not disturb it. Assume the block is displaced from mean position now. Assume the block is displaced from mean position by some distance y. Okay, because it's in the vertical direction, I'm calling it y. Okay, listen carefully. These are the steps that you need to follow. Let's say it is displaced by a distance y from the mean position. I am assuming it is pulled down. If it is pulled down, spring force will increase because the spring is getting stretched further. Spring force will increase. Mg will remain the same. So there will be a net force in the upward direction. Okay, we know that net force is upward. We have to write an expression for this net force. See, net force is opposite to displacement from mean position. So that minus sign is taken care of already. We just have to see whether the net force will be proportional to y or not. Okay. Now I want you all to tell me, what are the forces acting on the block? Respond quickly. When it is pulled down by some distance and released, what are the forces acting on the block?
So it's weight and spring force.
Okay, which force dominates? Which force dominates?
Spring force dominates.
Spring force will dominate in this case because the spring is stretched further. Okay. I'll just call it FSP, spring force. So now you can write the net force acting on the block as spring force minus mg in magnitude. Okay. Yusuf, tell me, what's the formula for spring force? Magnitude of spring force. Okay, any one of you, what is the formula for magnitude of spring force?
Spring constant into x.
Spring constant multiplied with, okay, you are saying x. What does x stand for? In the formula for magnitude of spring force, Kx, what does x mean?
So displacement from natural length.
Elongation or compression in the spring that has to be seen from natural length. How much the spring is stretched or how much it is compressed is what matters. So in this case, if you want to write the expression for spring force, it will be K multiplied with, see, at mean position, it was already stretched by x naught. There is a further stretch of y. So the total force exerted by the spring will be K into x naught plus y minus mg. This is the net force acting on the block. Y is the displacement from mean position. X naught plus y is the total amount by which the spring is stretched. Spring force depends on that. Fine. So the net force becomes kx naught plus ky minus mg. Now this does not look like it is proportional to y, but what is x naught here? Mg by k, or kx naught was already equal to mg. If kx naught is equal to mg, then we get net force is equal to ky. And the direction is opposite to y anyway. So the minus sign is taken care of. Now we see that the net force is proportional to y. What is y here? Displacement from mean position only, no? From the from the equilibrium position, we assume the block is pulled down by y. So y is the displacement from mean position, and we see that net force is spring constant multiplied with that y. Therefore, it executes simple harmonic motion. And again, the force constant, the proportionality constant between force and displacement from mean position is still the spring constant. So even if gravity is acting, even if the spring block system is oscillating under gravity, it will execute SHM with the force constant as the spring constant itself. This is the proof. The difference between horizontally oscillating spring block system and vertically oscillating spring block system is the mean position. For horizontally oscillating spring block system, natural length was the mean position. But here, equilibrium elongation, mg is equal to kx naught, x naught is equal to mg by k. That position is the mean position, and it will oscillate around that position. It won't oscillate around the natural length. That's the only difference. We get the same force constant here. Force constant is still the spring constant itself. Therefore, omega will still be under root k by m, where k is the spring constant. Time period will still be 2 pi root m by k, where k is the spring constant. So whether it is horizontally oscillating spring block system or a spring block system oscillating under gravity, time period will be 2 pi root m by k itself, if there's only one spring involved. Okay, the only difference is in the mean position. Now here also, you can solve questions like if the block is pulled by some distance and released, what speed will it gain when it reaches mean position? How much time it will take to complete oscillations? You can write the position time equation and such things. Okay. Only thing is that the mean position is not the natural length this time. It is shifted away from natural length. Okay. Let's discuss another system. Or, okay, let me give you one question. We'll see if you can apply all these fundamentals or not. Assume there's an inclined surface, angle of inclination 37 degrees, smooth, and let's say there is a spring block system placed on it. Okay. Spring constant, let's say, is 200 Newton per meter, and block's mass is 2 kg. Angle of inclination is given to you. Okay. Assume this block is released from or block is released when the spring is at its natural length. Now, I don't know whether that is the mean position or not. You should find out. Okay, it is released from this position. Now, you all quickly tell me, is this the mean position of the block? Will it not start oscillating if we release it from natural length? Will it oscillate or not? Or will it move away from that position or not?
Yes.
Yes. What force makes it move away from that position? Because spring is not exerting any force, it's at natural length. What force acts on it?
Yes, sir.
Can you repeat? Uh, it was not clear. Okay, anyway, it is mg's component which will pull the block away from that position. Correct. So this is not the mean position. Now, mg's component will be acting in the downward direction. That downward component will pull it away from that mean position. Will pull it away from this natural length. So the block will start moving. Spring will stretch. So at some position, spring force and that mg component will be balanced. That will be the mean position. By the time block reaches the mean position, it will have gained some velocity. It will cross that position and go to the other extreme as well. This system will definitely oscillate. Okay. Now what all I want you to find out, first thing, calculate the maximum speed attained by the block after it is released. We are releasing it from rest at this position. U is 0. Okay. After it is released, I want you to find out the maximum speed. I mean, in exam, the questions will be asked like this. You should understand that this is an oscillating system. You can write or you can consider it as simple harmonic motion. You have to find out what is the amplitude, what is the omega value. Those things you will have to do. Okay. Let me uh, take you step by step only. First thing, identify mean position. Next, check if it executes SHM. Next, if it does, how much is the amplitude of oscillation? How much is the maximum speed during oscillation? Okay. And time period of oscillation also. Time period you can easily tell, not a big deal. Okay. Solve this, all of you. I'll give you 3 minutes. Right. Tell me, is natural length the mean position of the block?
No, sir.
Fine. Did you identify where the mean position will be? Where the mean position will be means how much the spring has to be stretched. Did you find out? Okay. See, when the block is, or when the spring is at natural length, the block will be experiencing a force mg component in the downward direction. So there will be a net force along the incline in the downward direction. So something has to balance that. The only thing which can balance it is spring force. So some point below, some position below, the spring force will be balancing mg component mg sine theta. That is where the net force becomes 0 and that is the mean position. Fine. So you will have to write k x naught. Let's say the spring is stretched by x naught when the block is at mean position. Let's call this as x naught. Then spring force k x naught this time becomes mg sine theta. That's all. So you get x naught, the equilibrium elongation, as mg sine theta divided by k. That is the mean position. At that position, spring force and weight will be balanced. Weight component will be balanced. Net force will be 0. The other component of weight, mg cos theta, is already balanced by normal force. So you don't have to bother about that. Hope this part is clear. Next, have any of you checked whether it is SHM or not, and what did you find out? Okay, Vanilla, tell me how to check whether it is SHM or not. What are the steps we need to take?
So F should be directly proportional to the distance from mean position.
So you need to assume that the block is displaced from mean position by some distance. You can name the distance whatever you want. I'll call it as x itself this time. From mean position, let's say it is displaced by x. Now we need to write an expression for the net force acting on it. So you have to see what are the forces acting on it. Now mg cos theta normal force will always be balanced. The forces which are involved in, or the forces which do work in this case, are the spring force which acts in the upward direction this time. Why? Because the spring is stretched. So spring force will be acting this way. And mg component, mg sin theta, will be acting down the incline. Okay, so remember this, all of you. And this is how you should proceed, obviously. Because how do you check if it is SHM? The condition for SHM is that the restoring force should be proportional to displacement from mean position. So the first thing to do is identify the mean position. And from there, you assume it is displaced by some distance x. They won't tell you all that in the question. You will have to visualize it on your own. So let's say it is displaced by x. Now we need to write an expression for net force. That automatically becomes the restoring force. Now we know net force is in the upward direction here towards the mean position. You just have to see whether it is proportional to x or not. Now how to write net force? Spring force minus mg sin theta. Okay. Therefore, the net force when it is displaced from mean position is the spring force. Spring force formula is k multiplied with total elongation of the spring. Now, you know where the natural length of the spring is, and you know where the block is. The spring already had an equilibrium elongation of x naught. From there, we further elongated it by x. So what is the total elongation of the spring? X naught plus x. So k times x naught plus x, that is the spring force, minus weight component is mg sin theta. And we already know that kx naught is mg sin theta, equilibrium condition. If kx naught is mg sin theta, these terms will get cancelled and you are left with kx again. Now what was x? Displacement from mean position. So we see that net force does become proportional to displacement from mean position, and the proportionality constant is still the spring constant. Even this time, when it is oscillating on an inclined surface also, the proportionality constant is the spring constant itself. So condition for SHM is satisfied. Now we need the amplitude of oscillation. Can any of you tell me how much the amplitude of oscillation will be? In the question, it was told to you that the block is released from natural length. That's all. All these things we visualized. In the question, it was only given that the block is released from natural length of the spring. So, can any of you tell me how much is the amplitude of oscillation? Okay. Can any of you define amplitude? What is the meaning of amplitude? Vanilla. Or what do you remember about amplitude? See, amplitude of oscillation is the maximum distance an oscillating object moves away from its mean position. Now we have confirmed that this is SHM. In simple harmonic motion, amplitude is simply the distance between mean position and the extreme position. Okay. Now here we have identified mean position, this much, or this green line is the mean position. What about extreme position? Wherever the oscillating object comes to rest, that automatically becomes the extreme position. Now it was told to you that the block is released from rest when the spring is at its natural length. So this orange line itself is one of the extreme positions of the block. Okay. In fact, if you visualize this block oscillating, it will only oscillate this much. How much ever is the distance from extreme to mean on one side, same will be the distance from extreme to mean on the other side. So it will oscillate like this. Fine. Anyway, the position where the particle is at rest in SHM becomes the extreme position. So orange line is the extreme position, green line is the mean position. Distance between them is x naught. X naught we already know mg by k. Then this itself, sorry, mg sin theta by k. This itself is the amplitude of oscillation this time. Simple. Mass is given 2 kg, theta is given 37 degrees. You can substitute. So amplitude part is also done. Okay. Understand this. Amplitude, by definition, amplitude is the maximum distance moved away from mean position. So it automatically becomes the distance between mean position and the extreme position. Now at extreme position, particle is at rest. Here, initial position itself was the resting position. Okay. I should not call it resting position. At initial position itself, the particle object was at rest. From there, it started moving. Okay. So that initial position becomes the extreme position. And you know where the mean position is. Mean to extreme is the distance amplitude. Okay. Next, maximum speed during oscillation. Can any of you tell me an idea to calculate this? Maximum speed during oscillation.
So speed is maximum at mean position, so we can find out the velocity at mean.
Speed is maximum at mean position. So whatever is the speed there, that itself is the maximum speed. How to find out the speed there? Your idea is correct. Maximum speed occurs at mean position. How to find out how much speed it has there? Okay. See, you can use energy conservation, but in this case, it becomes more difficult to apply mechanical energy conservation because spring force is doing work, gravity is also doing work. So when you apply mechanical energy conservation, you need to write potential energy of spring plus gravitational potential energy plus kinetic energy of the block initially is equal to potential energy of the spring plus gravitational potential energy plus kinetic energy of the block finally. So that will be a very lengthy equation to write, and from that you can get the speed. But we have confirmed that this block executes simple harmonic motion. Now you go back to the mathematical equations that we derived for SHM. The position time equation or the displacement time equation was like this. X is equal to a sine omega t plus phi. The velocity time equation was like this. A omega cos omega t plus phi. And acceleration time equation was like this. Minus a omega square sine omega t plus phi. Now from this you tell me how much is the maximum speed in SHM? What is the maximum value of this velocity function?
A omega.
A omega. So if you are sure that it executes SHM, then the maximum speed can be directly written or calculated as A omega. Now we already know amplitude mg sin theta by k. And how to get omega for this system? See, we have determined that the force constant is the spring constant itself. We know k and we know the mass of the block. So we know omega of this system under root k by m, which is again 10 only because k is 200 and m is 2 kg. Yeah. So omega is 10. Amplitude in this case is mg sin theta by k. Let's calculate how much that is. Mass is 2 kg, no? So mg is 20. Sin 37 is 3 by 5 divided by k is 200. Okay. 20, 200 is 10 times. 3 by 5 is 0 0.6. 0 0.6 divided by 10 is 0.06 meters. 0.06 meters means 6 by 100 meters. That is 6 centimeters is the amplitude. Let it be. We need it in meters only. So if you know amplitude and omega, you know the maximum speed during oscillation. So applying energy conservation will be lengthy to find out maximum speed. Applying ideas of SHM is easier. And you can also tell the time it takes to go from one position to any other position also. You know the position time equation, you can make use of it. 1/4 of time period, or in terms of time period also, you can give the answer. Fine. Okay, so we discussed some cases of oscillation of spring block system today. First was oscillation of spring block system on a smooth horizontal surface. We saw that the Force constant is the spring constant itself. Time period will be 2 pi root m by k. Next, we discussed oscillation of vertically suspended spring block system. There also we saw that the force constant is the spring constant itself, and time period of oscillation will still be 2 pi root m by k. The only difference between horizontal and vertical system is the mean position of the mean position, or where the mean position lies. That's the difference. Same with oscillation of spring block system on a slant surface also. The mean position is the only difference. The rest of it is the same, time period of oscillation and all. Okay. Now, in any case, time period, which is 2 pi root m by k, or generally 2 pi by omega, where omega is under root k by m, time period never depends on amplitude. So whether it is small oscillations or slightly larger oscillations of the spring block system, it takes the same time. Because see, when deriving time period, did we ever bother about where the block is released from? No. How do we derive time period? What are the steps to derive time period? We had written today itself, no? We'll check whether it is SHM or not. How to check whether it is SHM or not? You'll assume it is displaced by some random distance x from the mean position and write the net force in terms of x. So amplitude is not involved here. Next, omega becomes under root k by m, where k is that force constant, m is the mass of the block. Amplitude is nowhere in the picture. Then time period becomes 2 pi root m by k, 2 pi by omega. So remember, time period of oscillation never depends on the amplitude. So whether amplitude is 1 centimeter or 2 centimeter or 5 centimeter, the spring block system takes the same time to complete oscillation. Now you may ask, sir, 1 centimeter oscillations are small oscillations, 5 centimeter oscillations are much longer oscillations. How can it take the same amount of time? See, suppose this is the mean position, and let's say one object is executing oscillation between these two positions. Okay. Now, how much time it takes to complete oscillations depends on how rapidly it gains velocity and moves from one position to the other position, right? Now, when the displacement is small, the force acting will be small. Because in SHM, the restoring force is proportional to displacement from mean position. So when displacement is small, the force will be small. So this particle oscillating between these two positions accelerates very slowly. So it takes a certain amount of time to do the oscillations. Now you consider another particle oscillating between these positions under the same force, same mass, same force. Let's say it is doing much larger oscillations. Now, if the force is same and the mass is same, I mean, force same, I mean, the equation of force is same. F is equal to minus kx. The magnitude of force definitely depends on the displacement from mean position. Now, for the green particle, if you take, it has much larger displacement from mean position, so much stronger forces will be acting on it, which will make it accelerate faster than the blue particle. Okay. So whether it's the blue one or the green one, if the restoring force is the same and their masses are same, they will take the same time to oscillate. Time period of oscillation of a system does not depend on amplitude. Keep that point in mind. Time taken to complete some part of the journey may depend on amplitude, but the time taken to complete the oscillation will definitely not depend on amplitude. Not just in a spring block system, even in other cases where oscillation happens, you will understand that time period will not depend on amplitude. Okay, let's look at one more system which can perform oscillations, and we will check whether it is simple harmonic or not. Consider a ring. Okay, let's say its mass is m, radius is r. Assume the ring is fixed. Okay. Now, on the axis of the ring, let's say a small particle is released. Particle of mass m is released from some distance. Now, ignore or consider only the gravitational force of attraction between these objects. So assume Earth is not present. Okay, Earth's gravity you ignore, but consider the gravity between these two objects. Now, ring is fixed, it cannot move, but the mass is released at some distance. Can any of you tell me what is going to happen to this system after it is released? Or will nothing happen? Earth's gravity is ignored, but consider the gravitational force between the ring and the particle. Based on that, you tell me what will happen after this system is released. We had come across such situations in the chapter gravitation. We solved some problems also based on this. Okay. The ring will attract the particle. Every mass attracts every other mass in this universe through gravitational force. The ring will attract the particle. As a result, what will happen? The particle will start gaining. As a result, the particle will start gaining velocity. Okay. So it reaches the center of the ring with some non-zero velocity. When the particle is on the right side, the force will be acting to the left because the ring is on the left side. It will be attracting the particle. It will gain some velocity and reach the center of the ring. When it is exactly at the center of the ring, the particle has some velocity. So it crosses over to the other side. And when the particle goes to the other side, the attractive force of the ring is to the right side. So what will happen? The particle will slow down and stop somewhere on the other side. But after it stops also, the gravitational attraction of the ring will continue acting on it. So it will start moving back. The particle will oscillate back and forth under the influence of gravitational force of this ring. So oscillations will take place. We need to check whether that oscillation is simple harmonic or not. Okay. At least tell me this. Where is the mean position of this particle? Means on the axis of the ring, at which position should you release the particle such that it does not start moving? Yusuf, where do you think the mean position lies? From where can we release this particle such that it does not oscillate? Vanilla?
Sir, at the center of the ring.
At the center, correct. Therefore, this becomes the mean position. Fine. Now we know that this particle is going to oscillate. We need to check whether the oscillations are simple harmonic or not. So what to do? Assume the particle is displaced from mean position by some distance x. You have to write an expression for the force acting on it now. So we need to write an expression for gravitational force between the ring and the particle. Do any of you remember how to do that? Can we use gmm by x square? Gm1 m2 by x square. To express gravitational force between the ring and the particle, can we use gm1 m2 by x square, the basic formula for gravitational force?
No, sir.
No. Why?
No, because the ring is not a point force.
Correct. Gm1 m2 by x square is valid for point masses. The ring is not a point mass. Then how to express force between a ring and a particle? Gravitational force between a ring and a particle. You have to make use of gravitational field. Gravitational field, by definition, is gravitational force per unit mass. So gravitational force becomes mass multiplied with the field. Now mass is the mass of the particle. Field is field of the ring. And gravitational field of a ring, if you remember the formula, it is gmx divided by r square plus x square whole power 3 by 2. We had derived this in the chapter gravitation. It's okay. Revise it once. Therefore, the force acting on the particle now becomes field. Field is G capital M x divided by r square plus x square whole power 3 by 2 multiplied with the mass of the particle small m. Therefore, the force becomes Gmm x divided by r square plus x square whole power 3 by 2. We wrote, or what we have expressed, the force acting on the particle as a function of displacement from mean position, that is x. Okay. Now you look at this force equation and any one of you tell me, is force proportional to displacement according to this equation? Is it of the form f is equal to some constant multiplied with x? Is there direct proportionality or not, according to this equation?
No, sir.
No, because x appears in the denominator as well. So this force does not seem to be, or not does not seem to, this force is not proportional to displacement from mean position. Therefore, it is not simple harmonic motion. It is oscillatory motion. It will have a period of oscillation also. Regular intervals it will take to oscillate back and forth, but it is not simple harmonic. Okay. But can we make it look like simple harmonic? That can be done. Suppose x, the displacement from mean position, is very small compared to the radius. If x is very small compared to radius, then what can we do? R square plus x square can be approximated to r square itself. Because x is very small. When you add a very large number to a very small number, the sum will be equal to or almost equal to the very large number. It won't make much difference. So r square plus x square is approximately equal to r square. Then the force becomes g mmx divided by denominator r square whole power 3 by 2 r cube. Now you see that the force is proportional to x. Therefore, generally this is not SHM, but for small oscillations, this is SHM. Okay. In case of small oscillations, this particle will execute simple harmonic motion. And you got force proportional to displacement. So this now becomes the force constant. K. And you know force constant and mass. If you know K and M, you can tell omega, you can tell the time period of oscillation. Fine. In question also, they will ask like this only. Find out, directly they'll ask, find out the time period of small oscillations of this system. You have to follow all these steps. You should first visualize why it executes oscillations. Then you should try to express force in terms of displacement and check whether it is SHM or not for small oscillations. It will be, and from that force constant, you can tell what is the omega value and what is the time period. Okay. So next 1 or 2 classes will be working on these only. I'll give you different systems and you will be finding out the time period of oscillation of those systems. Okay. Thank you all. We'll continue in tomorrow's class.